Hello and welcome to my talk. My name is Anna Werkovits and I'm pleased to share our theoretical work about the kinetics of organic-inorganic interfaces with you. Such interfaces form by the adsorption of organic molecules on inorganic substrates, and they typically exhibit a rich polymorphism. So, for example, planar molecules often prefer to build structures that consist of lying and of standing molecules. Due to different bonding mechanisms, interface properties often significantly vary between these structured classes. Therefore, controlled growth is essential for designing interfaces. However, when growing in thermodynamic equilibrium, a much smaller part of the spectra of interface properties is accessible than if we're harnessing kinetics. For multiple systems, it is thermodynamically favorable to adsorb in a lying orientation for low molecular dosages and to stand up for increasing dosages. For our model system, tetracyanoethylene on copper 111, theoretical and experimental studies indicate this transition as well. Even at further deposition, the formation of a second layer on standing molecules is thermodynamically favorable. In addition, the work function is increased by 3 electron volts after this transition, which is a lot. But can this transition be kinetically inhibited during growth? And if we really want to know at which temperatures molecules in the first layer remain in a lying position. And these two questions I want to answer in this talk. And for the curious listeners, this work was recently published in ACS Physical Chemistry Gold. For a trapping of lying structures, the following requirements must be fulfilled. First, to enable ordered growth, diffusion of lying molecules must be faster than the deposition. Second, to hinder the standing up during the growth, the formation of the second layer must be faster than the reorientation process. Then we assume that the lying molecules are trapped in the first layer. But if individual molecules stand up spontaneously, the falling down must be faster than an aggregation in the standing orientation. But how to model the kinetics of these processes? In a physical vapor deposition experiment, molecules first of all absorb on the empty surface, diffuse, aggregate, and spontaneously stand up and fall over again. Once a sufficient amount of standing molecules aggregated, the standing structure becomes favorable. Nevertheless, the hard limit for the rate at which standing structures form is the rate at which one individual molecule reorients. But due to the strong molecule-substrate interactions that are typical for the model system and its cousins, modeling involves high costs as density functional theory has to be applied. In our case, we apply the PBE functional and use T-serve as a dispersion correction. In order to make this problem now solvable, we make an approximation and estimate the limiting rate of lying standing transitions based on the kinetics of individual molecules. To calculate the transition rates of individual molecules, we use the harmonic transition state theory. Therein, the rate for the transition between an initial and a final state is calculated from the product of the attempt frequency and the probability of success, which contains the temperature and the energy barrier. So let's have a look on the schematical energy landscape between the two minimum geometries. Here, a lying and a standing one. The energy barrier for this transition is purely the difference between a transition state and the initial state. And in this work, we use the nudged elastic band method for the transition state search. I show you the actual results for the reorientation process. We see here now how an individual molecule stands up in its energetically most favorable way. When connecting now these geometries with their adsorption energies, we see that the reorientation occurs in a two-step process, so there is an intermediate minimum present. And nevertheless, we assign an effective energy barrier of 0.58 electron volts to the joint process of standing up. This is valid under the assumption that the lying molecules and the one of the intermediate state are in a pre-equilibrium. When we reverse the process now to check for the lying down process, the barrier for leaving the upright standing position is 0.05 electron volts, which we define as the barrier for the joint process for lying down. It's about 10 times smaller than the one of the standing up process. And we can now compare the energy barriers of the standing up and the lying down processes with the ones for the diffusion. To the process discussed, we identified 5 elementary diffusion processes in both molecule orientations. For reasons of simplicity, only the limiting processes of the lying and the standing diffusion are discussed in the following. That are the ones which possess the highest rates or the ones with the lowest energy barriers in their motion class. The limiting barrier of the lying diffusion is by more than 0.1 electron volts smaller than the one for the standing up. In contrast, barriers of the standing diffusion are with 0.06 electron volt, similarly small as the one for the lying down. In a final step, we can approximate the rates at which these limiting processes occur during growth, and how these rates change with temperature. In an experiment, deposition typically occurs in time frames from minutes up to a day. Accordingly, we can assume a transition to be hindered if its transition rate is smaller than a deposition rate, which is here in a hard limit the rate of one transition per day. So, let's have a look on the transition rates of the limiting processes for each motion class. We see that the lying down and the standing diffusion are clearly the fastest processes, followed by the lying diffusion and the standing up. Now, it is also clear that if we want to achieve a kinetic trapping of the lying structures, temperatures between 110 and 160 Kelvin have to be used during deposition. For example, let's propose a temperature of 140 Kelvin during growth. Here, molecules are likely to reorient in the order of only once per year, whereas they would fall over again within nanoseconds. The rate of the standing diffusion is as well in the range of the nanoseconds, but it's likely that molecules fall over much faster again than being able to diffuse and aggregate in a standing orientation. In the end, ordered structures of lying molecules should be able to form as well as lying molecules diffuse in the time frame of seconds. Now I conclude my talk. To answer the question if a kinetic trapping of lying structures is possible, we perform an individual molecule approximation on the kinetics of the system of tetracyanoethylene on copper 111. With this approach, we predict that the reorientation can be kinetically inhibited in the range of 110 and 160 Kelvin. Below, growth will be disordered and above thermodynamic equilibrium is reached. So, thank you for listening, and if you have any questions, please do not hesitate to ask.